All right, so let's talk about friction. So here is a wondrous artist's rendition of two surfaces in contact, block on a block, if you will. And what you can sort of see, because it's an uneven dented box here, but if we were to say zoom in on a region here, all right, so I'll zoom that out there. What we would really see in this region, we would see some jagged sorts of things. So this top part would kind of look like that, and this bottom part uh, would look like that. That's really what we would see if we could zoom in microscopically and see those surfaces in contact. All right, and there'd be a little bit of space in there. Okay, so reality is kind of what you see on the left. Get the right equipment, you can say, oh, wow, these surfaces really aren't as smooth as they feel or appear with my eyeballs. There's actually a whole lot of um, variability in that surface. And I would encourage you to think of what you know about chemistry and these electron atom models and whatnot, molecules, and or think of anybody ever have or seen those they're like bead carpets. It's like a carpet, but it's made out of beads, really. And so I don't know what good they are, but people make them. And if you imagine you had a one carpet made out of one size bead and another carpet made out of a slightly different size bead, and you tried to run them over, there would be all this bumping and falling into the grooves thing. Or even if they were the same size, you'd still have this bumpy thing as it went over the edges. Okay, so you could imagine friction that way, or like this. And so one of your handouts has a nice picture of this as well, and uh, something to the effect of this. So what I want to do is kind of oversimplify um, the business here. So this would be surface one, okay, and then this will be surface two, the uh, opposites there. So I will uh, oversimplify this for the sake of our analysis. So surface one would be jaggedy as such, and surface two, I could make it equally jaggedy. Okay, so we have these two surfaces here, and if I want to say that, all right, uh, we'll say that the speed of surface two is to the right, and it's not zero. Okay, so we have this motion here. So uh, the leading edge interactions are going to be more intense than the trailing edge. All right, so let's think uh, about that. So let's say right here, this will be a leading edge, and of course this will be a trailing edge. So as these things interact, so I'm going to have force interactions like this. All right, so that leading edge is going to be jamming into the of surface one. So I have uh, on I have the a contact force of surface one on surface two. Okay, so here's surface one, here's surface two. And so that leading edge has that pull, it's pulling on it. Now, though I've separated these surfaces in this sawtooth diagram, I'm really, they're touching, there's contact there. And so when that thing falls into that groove and it's being pulled on it, okay, most of the force, the larger forces are in one direction, okay? But then there are some smaller forces on this trailing edge, okay, like that. So we would have a trailing edge force, okay, a contact, a surface one on surface two, all right? One of them is bigger than the other, which means there's a net effect to be concerned with. Now, in reality, at every micron, it'll be like this much. It's constantly changing, but there's going to be this kind of 90-degree range of that leading edge force that will be offset a little bit by the trailing edge force. Okay, but it's never going to be uh, straight up, or very unlikely to be straight up or purely straight down. It's always going to be somewhere in between as we model it. So if I were to say, on average, okay, there's this, because let me draw this picture here. So I have one of these red forces, okay, that's one of the leading edge forces, and I have one of these trailing edge forces. That means that I have kind of on average something like this. Now we're not being perfect, we're just trying to create a general model. So this leading edge force, trailing edge, this is just we'll just call this our average. This is the force of contact, surface 2 on surface 1, average. So it makes sense that on average, it's just we could just kind of put it anywhere in there, right? Now, we don't have the tools to measure this exactly in our lab, but other places do have fancy toys, your tax dollars at work, et cetera, et cetera. So I have this. Well, Newton's third law tells me something. It tells me for every action, there's an equal and opposite reaction. So there's actually an opposite to this force, and it would be the other way. This is the reaction force, or it's a contact force of surface 2. Whoops, I gotta be careful here. Make sure you fix this. Glad I'm catching these. This is surface 1 on surface 2. And then this down here is the reaction force is surface 2 on surface 1. Surface pushing back. How do I know this? Well, Newton's third law says it, but typically speaking, you drag two surfaces, one surface along another, it doesn't fall through that surface. If I drag something along the floor here, the floor is not going to have a groove in it, unless it's an anvil or something like that digs into it. Typically, you don't see the surface destroyed, which means it made it. Okay, there was a reaction force that pushed back. That's why it stayed to smooth surfaces. So this little thing here about modeling gets us to just the idea of oversimplifying the surface interaction. So that block on top is pushing down into the block on bottom because it has weight. And so the weight force always has an equal and opposite reaction from the surface beneath it. But it's also when you start moving it, then you have this offset. So friction is a force. How do we measure it? How do we model it? That's the point here. All right, so let's continue here. So if I were to kind of think of that block on a surface, so here's some mass, all right? And if I were to force diagram this mass, it would have a weight force, but then there would be this is our surface, so this contact force of the surface on the mass. Well, we call this the normal force. Use a lowercase n, all right? Normal meaning perpendicular. We have like, I don't know, 50,000 different ways to say perpendicular. Yeah, perpendicular, orthogonal, normal. I mean, there's all these ways that we like to talk about what a perpendicular 90-degree angle to something. So this is normal to the surface. Just a straight up force there. However, if a force comes to town, an applied force, we know that assuming that force is capable of changing the position of this object, we will assume that it is. But even if it isn't, it would be because there's a frictional force. And by convention, we talk about frictional force as little f. So in the friction game, we like to use a lowercase f for friction force. Big case F for general force, summing of forces, Newton's second law business. So we have that. All right, so let's take a swing at this. So if I were to put the forces into a force diagram, I have the normal force pointing straight up. I have this friction force opposing motion. So a friction force will always oppose an applied force in the opposite direction. So if I push this way, there's going to be a friction the opposite way. We sort of know this, it's semi-natural. Well, guess what? That's a force diagram. And guess what we just figured out a minute ago? Is that there is this reaction force from the surface. So in reality, what I really have, if you remember, this was my contact force of the bottom surface acting on the mass or the upward force. What I really have is this. That's what I have in reality. Okay? And so friction, when we say friction is that way, we are taking the horizontal component of that actual reaction force. All right? So it's not like friction actually only pushes horizontal to the surface. It's actually a projection because we just figured out that there's this average jamming into the floor force, but it's actually inside of this 90-degree puzzle. Sometimes it might be really close to horizontal, or it might be really close to purely vertical, but on average, it's going to be somewhere in between. So we can draw a triangle like this, and what we call the friction force is really the projection of that actual force, and it allows us to do this math. And so friction works this way. Now that it's a simple little right triangle, guess what we can do? Well, what trig function would relate the non-hypotenuse sides of this triangle? Tangent, there's only one that would ever relate the non-hypotenuse sides, because sine and cosine necessarily have h in them, and ka, but the TOA has none of that. So the tangent of theta is going to be the opposite, or this friction force I just created over the normal force, which means friction will be in tangent theta. But what did we call n? Isn't it the case the acceleration 0, right? So that means the sum of forces would be normal force minus mg equals 0. That means n equals mg, which means friction will be mg tangent theta for this simple non-inclined block thing. All right. So we've developed a force law for friction, but we don't just leave it there, because that would be too simple. Tangent, okay, what we will do is friction equals mu n. Mu being the coefficient of friction. So wood on wood has a coefficient of friction. Plastic on wood has a coefficient of friction. Steel on plastic has another coefficient of friction. Typically, they're all between 0 and 1. Every now and then we have something weird that's more than that. And so mu, that's the conventional symbol for coefficient of friction. We'll have two kinds of friction: static friction and kinetic friction. Static meaning just when something's just sitting there and it's hard to push, getting it to overcome that initial friction. Kinetic friction is the friction you have once it's moving. Which one of these is going to be bigger, static or kinetic friction? Static, because it's easier to keep something moving than it is to get it moving. And that's because of friction. Static friction is that initial, and once it's moving, then it's easier to keep it moving. Okay, so more on the static versus kinetic at some other time.